Alright, welcome to topic 6, equilibrium, acids, bases and titrations. So as always, this is intended to be used as perhaps a revision rather than a alternative to attending the lectures. Okay, so topic 6, equilibrium, acids, bases and titrations. So we'll begin by discussing the equilibrium condition. You can see here we have a chemical equation. So H2O plus CO, and then we've got these arrows, double harpoons, okay, the equilibrium arrows they're different from resonance arrows, you can see, gives us some H2 and some CO2. Okay, now what we're saying by using these double harpoons, these equilibrium arrows, is that this process is in fact reversible. Okay, so we've got a reversible process here. So if you imagine initially, in the initial condition, we've got none of the products present. So what this means is that if you imagine the reaction has just started, you've added in your H2O and your CO, so your water and your carbon monoxide, and you've left them in your reaction container, your reaction vessel, and initially there's going to be no products being formed right at that initial moment. They haven't had a chance to form, no time has passed. But as time passes, the forward reaction will proceed. When we say the forward reaction, we mean the reaction that goes from left to right. So the forward reaction proceeds, and the concentrations of those products, H2 and CO2, they build up, they get greater. Okay? And the rate of the reverse reaction also increases, because as those products are forming, when they're present, that reverse reaction, that right to left reaction, can start to proceed as well. So there's two reactions here. There's the forward reaction from left to right and the reverse reaction from right to left. And as the concentrations of those products build up from the forward reaction, they're actually the reactants for the reverse reaction. Okay? So eventually the concentrations reach levels where the rate of forward reaction equals the rate of reverse reaction, and at that point the system has reached equilibrium. Now the thing is, that's not always going to be a 1:1 mix or a 50-50 mix. You're not going to always have the same concentration of starting materials as you do products. Okay, you're not going to have always the same concentration of the molecules on the left hand side as you do the molecules on the right hand side. The concentrations aren't always going to be the same. So the equilibrium position, in other words, could be to one side or another. So the forward reaction might be more favoured and the reverse reaction might only be a minor reaction, or it might be the other way around. Maybe the forward reaction isn't favoured. Maybe it's 99% in favour of the reverse reaction. Okay? Whatever that position may be, given enough time, the system will reach equilibrium. And this is when the forward reaction rate equals the reverse reaction rate. So in order to describe whether the reaction lies to the left-hand side or the right-hand side of the arrows, we use a constant value called K, the equilibrium constant, and based on the value of K, we can determine whether there's more of A and B in the reaction vessel at any given time, or there's more of C and D in the reaction vessel at any given time. So because we usually read from left to right, you'll notice that I have a tendency to call the left-hand side the products. The left-hand side will be the reactants, and the right-hand side will be the products, because that's the way it normally is. Obviously, because these reactions are reversible, and in fact there's two reactions proceeding, okay, we know that everything is both a product and a reactant depending on which way the reaction is proceeding. But to keep things simple, I'll refer to A and B as being reactants and C and D as being products. Okay, so we use K, and K is equal to products over reactants. So the concentration of products over reactants. Okay? And it can only be applied to systems with gases and aqueous states. If it's in the solid state or the pure liquid state, we can't have a K value if all of the species are in these states. If one or two of them are in these states, you ignore them. You leave them out of the equilibrium constant expression. And it will always be this way. So K equals the concentration of C raised to the power of lowercase c. So lowercase c in this case is the coefficient. So if you've got 2c, if the coefficient is 2, then we'll square it. Then we multiply that by the concentration of D raised to the power of lowercase d, and lowercase d is the coefficient again, divided by the concentration of A raised to the power of lowercase a, which is the coefficient, multiplied by the concentration of B raised to lowercase b, which is the coefficient. So, let's have a look at an example. So if we've got a reaction where it's a reversible reaction, so it's going to have an equilibrium constant, and the reactants are 4NH3 plus 7O2 gives us 4NO2 plus 6H2O. And these are all gases. So all of these are in the gaseous state. Okay. So remember, it's products over reactants, or it's C and D over A and B. So because we've got 4NO2, obviously we're going to raise the concentration of NO2 to the power of 4. And we've got 6H2O, so we're going to raise, we've got 6H2O, so we're going to raise our concentration of H2O to the power of 6. Let's have a look. So that's exactly what we're doing. So it's the concentration of NO2 to the power of 4 multiplied by the concentration of H2O to the power of 6 divided by the concentration of our NH3 to the power of 4 multiplied by the concentration of O2 to the power of 7. Notice that we use square brackets around our molecular formulae to indicate that we mean the concentration of. So those square brackets mean concentration of NO2, concentration of H2O, and so on. Now this is our equilibrium constant expression. What we can actually do is, if we have actual values for these concentrations, we can put those into the equilibrium constant expression. So if any given point, at some point in the reaction, the concentrations of these different species were measured. And what we're saying here is that we've got 2 mole per litre of NH3, 1 mole per litre of O2, 1.5 mole per litre of NO2, and 4 moles per litre of H2O. So we can put these numbers into the equilibrium constant expression, and we can actually get a value for K. Now in this case, K is 1,296. Now, because K is above 1, that means we must have had a larger value on the top, the numerator, and a smaller value on the denominator, which means in this case our products are favoured. Our NO2 and our H2O are going to be in higher concentrations. Okay. So if a change is imposed on a system in equilibrium, the position of equilibrium will shift in a direction that tends to reduce the change. This is Le Chatelier's principle. Now let's have a look at the effects of changing concentration. So here we've got a relationship. N2 plus H2 gas gives us NH3, and it's reversible. Notice that this isn't balanced, but if it were balanced, it would still work. This example would still work. Okay, so what's happening if we increase the amount of nitrogen, N2, we're going to shift the equilibrium position to the right-hand side, which means we're going to produce more NH3, and we're going to use up some H2, and compared to the starting conditions, the concentration of N2 is going to be increased as well, because we've added some more in. So there's plenty of examples of these that you can practice in the tutorial questions, okay, and we'll practice some of these in the lecture as well. So it's a great idea. The best way to get used to these is a great idea to practice lots of questions, okay. So this is what's happened. So the initial equilibrium mixture of N2, H2 and NH3, we've added some N2, some nitrogen gas, and we've got a new equilibrium position for the system containing more N2 due to the addition of N2, less H2 and more NH3 in the mixture than in A. So let's have a look at the effects of change in pressure. So if we've got these three species in a vessel, N2, H2 and NH3, we might increase the pressure or we might decrease the pressure. What we'll see is that, now imagine this is balanced. We're going to have N2, we're going to have 2 NH3, and we're going to have what's going to be in front of the H2, we're going to have 3 H2, okay, if we were to balance this equation. So what's going to happen is if we decrease the volume of the container, that means we're increasing the pressure essentially, we're going to favour the side of the reaction, be that the left hand or the right hand side. We're going to favour the side that has the least number of moles, and because there's the least number of moles over on the right hand side, that means the position is going to shift to the right hand side, and we'll see that the system now contains more NH3 and less N2 and H2. And you can see how this process would be industrially important. This information would be important in industry if you were trying to produce some ammonia gas. You know that increasing the pressure is going to give you a better yield. Okay, so here's a graphical representation. We've increased the pressure and now we've got a higher concentration of NH3 being formed after the increase in pressure. So the reaction shifts to the side, which is the right in this case, the side with fewer molecules. Let's have a look at the effects of change in temperature. If we now add or subtract some heat from the reaction. So we're given some more information now, okay? We've added something. What have we added? We've added plus 92 kilojoules to the right hand side. So N2 gas plus H2 gas gives us NH3 gas, and we've added 92 kilojoules to the right hand side. Because the heat is shown on the right hand side, thinking about the Ford reaction now, so I'll always discuss in terms of the Ford reaction. Thinking about the Ford reaction, is this process exothermic or endothermic? Is it giving off heat or is it gaining heat? Is it gaining heat from its surroundings? Does it feel cold to the touch or does it feel hot to the touch? This reaction would feel hot to the touch. If we were to touch it, it would feel warm because that heat is on the right hand side. It's a product of the Ford reaction, so it's actually giving off heat to its surroundings. Exothermic process. Okay. Now this energy, this 92 kilojoules, is treated as a product or a reactant, and then we apply Le Chatelier's principle. So what's going to happen if we increase the temperature? The reaction is going to shift to the left. Okay, increasing the temperature is going to shift this reaction to the left. If we decrease the temperature, it's going to pull the reaction over to the right. The equilibrium position is going to be shifted to the right. Now, if the reaction were endothermic, it would be different because we'd have the kilojoules on the other side. But if the reaction's endothermic, then the opposite would apply. Let's have a look now at the importance of water. So we've already discussed this, but water is a bit special in terms of its structure, its shape, its polarity. It's got special properties in terms of specific heat capacity. It's got a special ability to dissolve things because it can form these hydration spheres around ionic solids, for example. And when we have ionic solids dissolved in water, we're going to increase the electrical conductivity. So let's have a look at the nature of aqueous solutions. Now, we're going to be using, in part, the Arrhenius ionic theory. Now, this was introduced in 1887. This is the Arrhenius definition of what an acid is and what a base is. Okay, we'll discuss this very soon. Now, when we're discussing electrolytes, we can have strong electrolytes that have a complete dissociation. So if we have a look at hydrochloric acid being added to H2O, this is completely dissociating into hydronium ions, H3O+, and Cl-. So in this course, we will use hydronium ions and hydrogen ions largely interchangeably, okay? This is because the hydrogen ion cannot exist alone in a water solution. So when it's combined with a water molecule, it will form the hydronium ion. And weak electrolytes are only going to have partial dissociation. So these are the most common in our weak acids and weak bases, where only part of the compound is now dissociating and forming this acidic species. Now, in these two examples, we've got hydrochloric acid and we've got acetic acid. And you can see that acetic acid is only partially dissociated, whereas hydrochloric acid completely dissociates, which means we can use acetic acid. Acetic acid is in vinegar, so we can use acetic acid on our salad, but we can't use hydrochloric acid on our salad, okay? Then we've got the characteristic of a solution. So the extent to which a solution conducts electricity is directly dependent on the number of charged species present, okay? So by measuring the electrical conductivity, in some cases, we can get an idea of how far dissociated our species are. As we're discussing acids and bases, we're going to have to use some definitions. So there's the Arrhenius definition. Now this one is the one that's limited only to H+ and OH- species. So hydrogen ions and hydroxide ions. Okay. Water's interesting. Water's amphoteric. It's going to have properties of both an acid and a base. And of course the Arrhenius definition is going to be limited only to solutions. So they have to be aqueous solutions for this definition to be useful at all. Next is the Bronsted and Lowry definition, where acids and bases are defined as either hydrogen ion donors or hydrogen ion acceptors. So this broadens the definition. Okay, so we've got a much broader definition. So if something's a hydrogen ion donor, it can be a Bronsted and Lowry acid. And if something's a hydrogen ion acceptor, it can be a Bronsted and Lowry base. And this definition is now not just limited to aqueous solutions. In the Lewis definition, a Lewis base can be an electron pair donor. So species like oxygen or nitrogen are electron pair donors. And a Lewis acid could be an electron pair acceptor. So something like our H+, it accepts a pair of electrons. Now this is a broader definition again. Here's some pictures of some household products that contain acids and bases. As we've mentioned before, strong acids, so for example hydrochloric acid, sulfuric acid, nitric acid, these will fully dissociate. So if we consider our example with hydrochloric acid being added to water, and we're going to get a full dissociation into hydronium ions and chloride ions. we've also got weak acids as well as strong acids. So weak acids are going to partially dissociate. Okay, so for example, acetic acid and water is going to form again our hydronium ion and a conjugate base, which is the acetate ion, but it's only going to be a partial dissociation. So the equilibrium may lie to the left, strongly to the left, where the reactants are, whereas in the case of hydrochloric acid, it completely dissociates. There is no equilibrium, it's a complete dissociation, and this is the difference between a strong acid and a weak acid. Something that's useful to look at now is the dissociation constant for water, or Kw. So we had a look at K values earlier on. So water itself is amphoteric, so it can dissociate and form both an acid, H+, and a base, OH-, the hydrogen ion and the hydroxide ion. And we can take this relationship and find a K value, same way as we always do, and that turns out to be 1 by 10 to the minus 14. Okay, 1 by 10 to the minus 14. So it's a very low number. Obviously what this is telling us is that water doesn't spend a whole lot of its time being dissociated, okay? But it does spend a small amount of time. This 1 by 10 to the minus 14 is an important number for us though, because this defines the pH scale. This is the reason why the pH scale ranges from 0 to 14. The pH scale is a log scale. You've probably heard of pH before. So if you've heard of pH before, you're probably aware that a pH of 7 is neutral, below 7 is acidic, above 7 is a basic pH. Okay? As we get a lower pH, we're actually increasing our hydrogen ion concentration, and as we have a higher pH, we're decreasing our hydrogen ion concentration and now increasing our hydroxide ions. The pH scale only works in aqueous solutions. Okay? So if we have a look at what pH really means, it means the minus log of the hydrogen ion concentration. Minus log of the hydrogen ion concentration. So the lowercase p represents our minus log. The h, on the other hand, represents our hydrogen ion concentration. So pH minus log of hydrogen ion concentration. POH is the minus log of the hydroxide ion concentration. That little p, that lowercase p, always means minus log. So there is a relationship that pH plus POH must always equal 14. So if the pH is 3, then the POH must be 11. Because remember that Kw, the definition of Kw, or the value for Kw was 1 by 10 to the minus 14. And this is why we have this relationship where pH plus POH equals 14. Now, if you can't remember how logarithms work, if you were to take your calculator and just try log of 10, log of 100, log of 1,000, log of 10,000, and you should be getting values of 1, 2, 3, 4. We're counting the zeros. Now log scales, so a difference of 1 on the log scale is a 10-fold difference in hydrogen ion concentration. So if you've got two solutions and one has a pH of 2 and the other has a pH of 3, then one solution is 10 times more concentrated than the other in terms of acidity, in terms of hydrogen ion concentration. So strong acids will have a weak conjugate base, okay, and a strong base will have a weak conjugate acid. So when our acid dissociates, our hydrochloric acid for example, and we get some H+, we really know it's going to be H3O+, but remember I said we'd use this interchangeably, so H+ and some Cl-. That Cl- is a weak conjugate base, okay, and strong bases have weak conjugate acids. So our sodium hydroxide, okay, is going to form sodium ions and hydroxide ions. So where are we going to have our conjugate acid? It's going to be the sodium ion, and that's a weak conjugate acid. Equilibrium lies strongly to the right hand side, and we consider this to be a complete dissociation. Having a look now at a strong acid-base titration, these are used to determine the unknown concentrations of either a strong acid, as shown in the picture, or a strong base, which was now opposite to the picture. So you can see here we've got a perhaps strong acid that we're starting with. So notice that we're starting with a very low pH, and then as we're adding a strong base, the pH is increasing. There'll be a point where the pH equals 7 and it's neutral. This is known as the equivalence point because we're going to have the same amount of moles of our strong acid as we do our strong base in solution, assuming that we've got a monoprotic acid, for example, okay, and a base that produces one hydroxide ion. Now, if we're looking at a strong base titration, obviously we're going to start at a high pH because bases have a high pH, and as we're adding solution to it, the pH is going to drop and drop and drop, and again, we're still going to reach our equivalence point at pH 7. Now, why would anyone want to do this? This is great for determining the concentration of an acid that has an unknown concentration. So you might have a sample of acid, maybe you're working in a vinegar factory, I don't know, you're making vinegar, you want to know how acidic your vinegar is. By looking at how much sodium hydroxide you've added to the vinegar to reach the equivalence point, you can then determine what the concentration of the vinegar must have been, because the amount of moles of base that you've added, in this case sodium hydroxide, the amount of moles of base that you're added will equal the number of moles of acetic acid that was in the solution to begin with. So to calculate the concentration of the analyte in moles per litre, we can have a look at moles of analyte. This is a relationship. Moles of analyte equals the moles of titrant. Okay, so the moles of titrant equals the volume of titrant times the concentration of titrant. The moles of analyte equals the volume of analyte times the concentration of the analyte. Since Na equals Nt, the concentration of analyte, Ca, equals Na on Va, which means the number of moles of analyte on the volume of the analyte will give you the concentration of the analyte. Okay, so you have to make sure that first we balance the equation, we calculate the moles of titrant, so work out how many moles of sodium hydroxide we've added. Since the moles of analyte equals the moles of titrant, now we know how many moles of our acid we've titrated, and we know the volume of the analyte. So look at the volume of acid that you put in there, you can work out moles per litre. And this is something that we're going to be doing in the lab. So refer to your lab notes if you're getting a bit confused here. So you can work out the moles per litre of your acid of unknown concentration in this example. Okay, so in this case, where we've got an unknown concentration of hydrochloric acid, HCl, and we're adding sodium hydroxide to it. And when we reach that equivalence point, we can have a look at how much sodium hydroxide we've added. We can work out how many moles that is. That will tell us how many moles of hydrochloric acid we had in our unknown. We know how much of our unknown we've put in because we're the ones who literally, we measured out how much of that unknown acid. So we've got the volume, we've got how many moles it is. So moles per litre, okay, number of moles divided by how many litres you have, you can work out the concentration. Okay, and in this case, in this example, we had 0.02 litres or 20 millilitres, right? And the concentration was 1 molar. So this is referring to the sodium hydroxide. So that means we've put 0.02 moles of sodium hydroxide into the acid. And the volume of the acid was 10 millilitres. So we know now that we can take our 0.02 moles and divide that by 0.01 litres, 10 millilitres, 0.01 litres, and that means our acid must have been 2 mole per litre concentration. Okay, so 2 molar acid concentration. Now, how do we find the endpoint? We could use a pH probe and just see when we reach pH 7, or we could use a coloured indicator. We can actually add a chemical to our mix that's going to change colour when we reach a certain pH. Okay, and the one that we use commonly is phenolphthalein. And you probably noticed from this graph the phenolphthalein does tend to turn colour at a slightly higher pH than 7. So for those of you that are very observant, you probably noticed that this is a little higher than we would like, and this is the reason why in the lab we want to go for a very light coloured pink. Very, very light coloured pink, and that's going to be closer to pH 7. Here's an example of how our phenolphthalein might work, and you can see in this picture of the molecule over here, the colourless form has a different molecular structure to the pink form because what's happening is in the presence of that base, we're deprotonating and changing the conjugation of the system and allowing it to become coloured. Okay, don't worry too much about that if you don't understand. That's just for your interest. So this, you won't be examined on that particular point, but I think that's very interesting because we're deprotonating. You can see there at that phenol, those OHs on those benzene rings are deprotonated. We increase our conjugation, and now we've formed a coloured species. All right. And of course, there's different indicators that you can use for different purposes. Now, let's take a look at the equilibrium expressions for weak acids. Okay, so this is something a little bit new now. Equilibrium